Hi, welcome to the Cosmic Pie podcast. This is episode number 20. So I'm your host, Wayne Barkhouse, and with me today is
Robert Moore.
So Robert, can you believe there's been 20? This is our 20th podcast?
Sometimes I can believe it, and then other times I'm like, where did the time go? But it's been since January, so
Yeah.
6 months now.
Yeah, for sure. So the purpose of this podcast is to discuss things related to science. So that could be in the fields of physics, astrophysics, cosmology. You want to include that as well. Anything that you may want to talk about. We do have a live chat, so if you have any questions you'd like to have answered, it could necessarily not be on the subject area that we're talking about. So we will stop whatever we're talking about and check out your question and strike up a conversation related to that.
Yeah. I was about to say, sometimes that conversation might lead to another show, so keep that in mind as well. But
Exactly. Now, we are broadcasting live from the campus of the University of North Dakota here in Grand Forks, North Dakota.
Yep.
And approximately 15 minutes from now, we do have an event that's occurring in the skies above us. Do you want to mention what that is, Robert?
Apparently, celebrating so many years of air refueling, 100 years of air refueling. We've got some B-52s and CK-130s, I believe it is, going to be flying overhead. So, we're going to be down here in the basement of our building doing our podcast, but those things are awful loud, so we may get to hear them.
So we may or may not be able to pick it up on the podcast. So
right.
If that occurs around 15-minute mark, we'll know what it is, a deep rumbling sound.
Right.
That or the building's falling down, then you'll just see empty chairs because we'll be hightailing it out of here.
Yeah. Trying to get up out of the basement where everything else is going to fall into. Yeah.
There you go. Good time to say a disclaimer.
Oh,
You want to say it, Rob?
Let's see. What is it? The opinions expressed in this podcast are those of myself and Wayne. They do not reflect necessarily the opinions of the state of North Dakota, the University of North Dakota, the College of Arts and Sciences, the Department of Physics and Astrophysics. They're just us.
Yeah.
So,
The city of Grand Forks.
Grand Forks.
Any resident thereof.
Well, I reside there, so they're still my
Except for
area.
us, right?
Yeah.
Yeah. So, part of this podcast is to kind of look at things that are happening now in the news. So look at current events and then maybe give our opinion or our twist on the things that we see in the news.
Right.
For better or worse. And a lot of these news items that have come out in the last 6 months since we've been doing the podcast are related, of course, to the James Webb Space Telescope. And that's not surprising given the fact that it is a brand new telescope, the largest telescope that we have in space in the optical / infrared / far infrared. It's mostly an infrared telescope.
I was about to say, I don't think it has even...
It straddles a little bit in the far red part of the
Okay.
optical, with the shorter filters, wavelength filters that we could use. But it's mostly it's essentially an infrared telescope.
Yeah.
Right? That's the best way to think about it. And that's why the argument of putting the money towards the James Webb, and the idea is at some point the Hubble Space Telescope, which is primarily an optical telescope, will fail. And
Right.
that will mean we'll no longer be able to use the Hubble Space Telescope at some point if we don't continually go up to the telescope and somehow repair it. Now, there's this idea that NASA and SpaceX are exploring to go up to the Hubble Space Telescope, maybe in a Dragon capsule with some astronauts on board. You'd have to have adapters,
Right.
to fit so that you can link up, at least get close to the telescope to do station keeping, so you can, do some repairs on the Hubble. So I don't know what
Right.
that would look like, but they're exploring that possibility.
Things a lot of people don't realize is the cameras degrade after time here on Earth because of cosmic ray strikes to the silicon detector chip and things like that. And up in space, that's just that much worse. So space is a harsh environment.
Yeah, and the other thing is when you're using a telescope is you need to accurately point it at an object for a long period of time. And so the way the Hubble does that is through the use of a system of gyroscopes. So these are rotating devices. And because things are moving, they're mechanical devices that are in motion, they fail eventually, like anything else that has,
Right.
bearings, no matter how sophisticated they are. So the gyroscopes, think in total there are like 5 gyroscopes. Several of them have failed already, so we're almost down to our last one. If it fails, we have a problem where it becomes very difficult to point a telescope.
It tumbles at that point.
Yeah, we just can't point it accurately enough, and so
Right.
you get smearing in the images if you're doing long exposures,
Right.
and that's a major problem in this kind of thing. And so when those gyroscopes go, at some point you're done.
Right.
Right, it's game over. And so I know over the course of several repair missions to the Hubble, I think there were 5 in total before the space shuttle was retired, that amongst those 5 repair missions, several of the gyroscopes were changed out. So essentially, I think there are no original gyroscopes on the Hubble from when it was first launched in 1990, I believe it was.
Was it?
I think it's 1990, it's close to that. But,
Yeah, it would be close to that.
yeah, I know it was supposed to go
Yeah.
up in the summer of 1986.
Right.
And that didn't occur because of the Challenger blew up in
Right.
January of 1986, and that put all shuttle flights on hold for just over 2 years. So I believe it was 1990 by the time the Hubble Space Telescope was actually launched.
That would make sense. Yeah.
Yeah.
I
So
mean,
it's been up
not
a
like
while.
We couldn't look. But
Yeah, so it's been up a while.
Yep.
And so things do break. I mean, I know they switched out to solar panels and these sort of things. And
An
There's-
amazing instrument.
well, there's an interesting story with the solar panels. I don't know if you ever heard this. When the initial set of solar panels were put on the Hubble Space Telescope and they unfold them in space, when the telescope goes from the day side of the Earth and then goes into the night side, it's a lot cooler. You're talking about temperature swings of hundreds of degrees Fahrenheit.
Right.
Well, when you take a solar panel or anything else, like a metal, let's say, and you go from extreme
Yeah, see
heat
where
to
this
extreme
is going.
cold, the metal contracts normally.
Right.
It shrinks a bit.
Expands and contracts.
So as
Yeah.
the Hubble Space Telescope was orbiting in the shadow of the Earth and the coolness, if you like, low temperature environment, back into the sunlit part of its orbit, and the temperatures would be the highest heating it would experience, the solar panels were contracting in the cold and expanding in the heat. So this constant motion of contracting and expanding caused vibrations in the telescope.
Right.
And that actually affected the quality of the images,
Yep.
is my understanding.
Absolutely.
Now, there was damping mechanisms that was put on board the solar panels, right? For lack of a better term, pulleys and wires and these kind of things, shock absorbers, let's say, to try to minimize those type of vibrations. But they never quite worked the way that the engineers envisioned them to work on that first generation of solar panels.
Yeah.
So the story that I heard, I'm not sure if it's 100% true, but the story I heard is that the intelligence agencies of the United States, the spy agencies, the military, and so on, they had already had their own Hubble-like telescope in space,
Right.
except it wasn't pointing out to look at the cosmos, it was pointing down on
to
Earth
Yeah.
to look at, things on the surface of the Earth, right? Different countries and so
We
on
won't
and so
talk
forth.
about that.
Yeah, you can imagine use your own imagination for that. And they knew the problem with these large solar panels because apparently they had used that and found out they couldn't minimize the vibration to the point where they liked it. So they had changed up the engineering in the future. But all that information was classified. They
Right.
never told NASA. So
Right.
when NASA was initially designing the Hubble with these solar panels, somebody in the military or in the spy agency would have known, hey, you're going to have a problem with that because we've had a problem with it, but it's classified, so we can't tell you.
Right.
So they had to find out for themselves, this problem.
Yeah.
But I mean, that's normal, right? You build anything that's new, there's going to be bugs.
There's
right?
going
I
to
mean,
be
it's
bugs.
like
There's going to be
writing
hiccups.
code for computer. A lot of people are familiar with writing code nowadays. What's the chance of writing a big elaborate code and having it work perfectly the first time you run it? Yeah, almost zero.
Yeah.
Right? There's always going to be at least one bug, one mistake somewhere, or the code doesn't quite do the thing you want it to do in terms of its basic flow, its logic.
It's logic,
in
right.
that sense. So that's not unusual. So when the James Webb Space Telescope was being designed, put up, people knew that the Hubble had a finite lifetime like they all do. And because the James Webb was earmarked to be sensitive to the infrared, there were some grumblings, if you like, from some astronomers. What about the coverage in the optical? Because if the Hubble fails, we are done, right? We won't be able to cover the optical wavelengths with the same reasonable size space telescope. And so there was some argument about that. But I mean, it was designed initially to look at very high redshift objects.
Right.
That is, look at very early galaxy. You wanted to get back to the heart of galaxy formation.
That was really one of the primary design parameters.
That's right.
So,
And that would mean the telescope would have to be sensitive to infrared wavelengths.
right.
And the reason for that is because we live in an expanding universe. And because of that expansion, very distant galaxies, the main type of lines you see in their spectra that you normally would see in the optical, if they're at rest relative to us, so let's say nearby galaxies, those lines are all shifted to much longer wavelength. In fact, they're shifted so much so they're well out into the infrared.
Yep.
So you can't observe them not only on the ground because you're affected by absorption of infrared light, not totally, but mostly. It depends on what wavelength you look at exactly. So you want to get your infrared telescope in space, but those lines are shifted from the optical out into the infrared. So you got to look in the infrared anyways to see those lines coming from very high redshift galaxies. So you need an infrared telescope to explore the very early universe. Yep. Now, can you do anything else with that? Yeah, you can do lots of things with those type of telescopes. You can explore, for example, star formation regions. Mm-hmm. So we know that stars do not form in isolated areas of space where there's absolutely nothing around. They have to form from something, right?
Right.
So it's like a baby appearing out of nowhere. No, there has to be parents, right? There has to be some way of forming that baby, if you want to use a human analogy, right? Yeah. I'm keeping it clean, Robert. I'm keeping it clean.
No, I agree.
So stars then typically form inside of what we call giant molecular clouds. And one of the things, giant molecular cloud that's very popular, its name is very common, is the Orion Nebula. That's a beautiful target in the wintertime in the constellation Orion for amateur telescopes.
You can actually see that nebula with your unaided eye, by the way, if you're in a dark sky environment. And I always like pointing that out because the sword hanging from Orion's belt, that last star in it, it looks fuzzy. Well, that's because it's that nebula.
Yeah, it's a giant star formation region. Mm-hmm. It's roughly about 1,400 light years away. Now, there's some depth to it, right? It's not all at the same distance, right? It's a three-dimensional type of structure anyways. So there's going to be the near side of it is closer to us. The back side is going to be further away. So there's several light years. I don't know the thickness, on the order of 50 to 100 light years.
Something like that.
Yeah, because a giant molecular cloud, typical diameters is about 300, 500 light years, let's say. And if you assume this thing is a sphere, which is not, then that gives you then the line of sight thickness of the object is on the order of that, 300 to 500 light years. Okay, so it's roughly about 1,400 light years away. So if you're studying, and so we're not worried about focusing on very distant, very early galaxies, if you're looking at star formation sites, you want to undercover the process, what is the nitty-gritty details of how you form stars to begin with, looking at things like the Orion Nebula is a perfect place. Is it not?
Absolutely. It's first place. It's the first place Hubble looked, even.
That's right.
So, I remember being a young upcoming scientist in my bachelor's degree program. Hubble pictures started coming in, and one of the first things that they showed that made me just start going, wow, was a picture of the Orion Nebula showing all these little proplyds, as they're called, these places where stars are forming and have disks of debris around them. And it was like, holy cow, that's amazing. We can actually see where should be planets forming.
Yes, so you see evidence of young stars, and not only that, they're surrounded by the material from which the star formed from.
Right.
And that material then ultimately would turn into a solar system that particular star.
Right.
Now, whether they contain planets and how many planets and what are their different masses and so on, that's yet to be determined, right?
Absolutely.
And that would vary. That would depend on the exact details of how these things were coalescing and all these kind of things, So, and what material is available and the density of it and so on and so forth. All the nitty-gritty details of what would cause a solar system to form. And what we know for sure is, unlike our solar system, which has 8 planets, because we left off poor Pluto, right? We have, 4 main gas giants, Jupiter, Saturn, Uranus, and Neptune. Then we have the rocky planets, right? Mercury, Venus, Earth, and Mars. Okay, and we're leaving out Pluto on this.
Right.
Okay. So we just naturally assumed, before we knew the existence of planets around any other stars, that all solar systems were more or less look like ours, right?
Sample size of one bias, folks.
And that turns out to not be the case at all.
It's not what they look like at all.
So we know now literally of thousands of other planets going around other stars, And they don't look like ours in terms of their solar systems, their stellar systems in that sense,
Yep.
right? And so we know there's a whole range of variables that actually are important when you're actually forming a solar system to begin with.
Absolutely.
And that would give you the different, sort of flavor, if you like, the richness of the variation in the properties of the different types of solar systems that we find.
One of the big things they're actually trying to find now is moons around planets, because there's some that are beginning to wonder, for terrestrial rocky type planets, you might want to be looking for large moons around some of these gas giants. So that's one of the points that they're really looking at now is how can you spot a moon around one of these exoplanets.
Right, and I know for sure it's the extra reflection or extra, if you like, blockage of sun, it'd be starlight in that case, that you could see it in the so-called light curve, which is the plot of brightness and how it changes with time. That the nitty-gritty features in that, if you very precise measurement of brightness of stars, could elucidate those features that allow you to see that.
One of them I in fact know very well because did a whole section on it, and that's the Lassiter-McLaughlin effect.
Right.
That it puts a little jag in the bottom of a transit.
And you would expect that all planets, or at least most planets, are going to have moons.
Right.
I mean, there shouldn't be anything special about our own system, our solar system, that a lot of the planets.
I mean,
have
Saturn
moons.
has now what, 180?
Yeah, it's like the most moons in the whole solar system now,
Yeah.
right? And then second would be Jupiter. But,
So planets have moons.
yeah. So the only ones we know of that don't have a moon is Mercury, Venus.
And
That's
no,
it.
that's it.
Earth has a
Yeah.
moon, obviously. Mars has 2 moons, Phobos and Deimos.
Right.
Right? Jupiter has a slew of them, around 90 or so. Saturn, well over 100. Uranus has moons. Neptune has moons. And even Pluto.
Pluto has
Yes, let's
moons.
include Pluto, that dwarf planet. That even has moons.
Heck,
Pluto's a system.
If I'm not mistaken, Pluto's moons, some of them have moons.
Right, and we've seen
So-
that. We've seen some of the asteroids have moonlets going
Asteroids have
around,
moons.
right?
We did the DART mission that actually knocked a spacecraft into a moon around an asteroid.
Yeah, that was back in, I think, September of 2022.
Right.
And so that was part of that whole program, was to try to change the motion of one of the small little moonlets orbiting an asteroid.
Right.
And
Basically to see if we could adjust the path of an asteroid. And we wanted one that there was pretty much no chance of it being knocked out and
right.
possibly coming on an Earth crossing orbit. We scientists kind of know what we're doing. We
Yeah.
take things into account.
And that collision, by the way, that changed the orbital period of that moonlet by like 30 minutes.
By 30 minutes. Yeah.
So it just proved that we can
we can divert
move things. We can change
Yep.
the orbital path. So if something is heading towards the Earth, this is ultimately the ideal of that program, and why future generations of more sophisticated programs will be done, I'm sure, conducted.
Sure. Yeah.
Is that we want to be able to deflect, something that we see in the long range, that will get here in several years from now, to be able ever so slightly deflect the orbit or change the orbit slightly. So by the time it does reach the vicinity of the Earth, its orbit has deviated enough that there's no chance of colliding with the Earth.
Right.
So
That's the ultimate goal.
that's the ultimate goal. So we can prevent a real mass planet-killing extinction event, right?
Yeah.
That would totally eliminate all life on Earth, including us and cockroaches and all those other wonderful things,
Absolutely.
Yeah. So this whole process of looking for star formation, to understand that whole process, there was news about that recently. So if you want to go to the first slide, Robert.
Yeah. And
So there was a paper published in Nature, so it's just being published now. And if you read the title here, it says Formation of the Methyl Cation by Photochemistry in a Protoplanetary Disk. So these molecules are important, Robert. You want to explain why these are important?
The methyl cation is essentially the building block of all more complicated, organic molecules.
Carbon.
So it's a carbon atom with 3 hydrogens. It should have 4. That's why it's a cation. And so it's very reactive. It will latch a hold of the nearest carbon, and all of a sudden you get chains of carbon forming. And this leads to complicated and complex organic molecules, is chains of carbon.
So if you like chemistry, it's a CH3 plus
Absolutely.
molecule, right? Would
It's
be
a
the way.
CH3 plus.
Would be the way to say it, right?
And So yeah, this is the basic building block of all carbon chemistry, which we call organic chemistry.
Right. So this is telling us that all life forms like us, human beings, are carbon-based.
Right.
Right? So one of the questions we have is that is carbon ubiquitous in terms of the building blocks of these organic molecules out in space? We know they exist in the Earth environment, but do they exist out in space? And when you first think about that, you say, of course they have to. What's so special about our environment, right?
Right.
We just live on a planet that's in some solar system that, built around some just average star. There are hundreds of billion stars in our own galaxy. There's 1 trillion galaxies in the observable universe. There's got to be other carbon-based molecules that exist out there in the universe, right?
Right.
And we know that stars themselves give off carbon.
Absolutely. And when you go beyond that even, we've found the evidence of things like water in these cold molecular clouds that form stars. We found ethanol, we found methanol, we found formaldehyde. We see these things through their spectra. You'll hear us talk about that term. We've already talked about it. We will continue. So we see the evidence of these in those spectral lines. They absorb light at only certain frequencies, certain colors. And so this is how we're finding these things. This is it. This was great because, with the methyl cation, you can start putting together all kinds of things, including benzenes and ketones and acetates and acetones and all of those nice organic molecule combinations, including
Amino acids.
amino acids.
Now, these building blocks for life are important, right? How are you going to build a house if you don't have the building blocks, the construction material?
Right.
So how are you going to build life if you don't have the building blocks? Now, obviously, we don't know the detailed steps, or we don't even know the steps in coarse grain, if you like, of going from something that's not alive to something that's alive.
Right.
If I was to redo my career and I was forced to be a biologist, not that there's nothing wrong with being a biologist.
There's nothing wrong with being a biologist.
But if you are told that you have to be a biologist, what would you like to study? I would say I want to understand how you go from non-life to life. How you go from non-living to living.
Right.
That is, to me, personally, that's one of the greatest mysteries in biology. And it's a mystery that surrounds complex systems.
Right.
As a physicist, as someone who studies astrophysics, for example, we like to get down to the fundamental nature of things. But we know that there's things like us that are built from highly complex systems, right? You can say, oh, Robert, there's nothing special about you and I. We're just built up of ordinary atoms.
Right. I mean, I can give you an example of this, not dealing with life or biochemistry, but in my class on stellar atmospheres, we started out assuming something called local hydrothermic equilibrium. And everybody in the class was like, why would we do that? We know that even a nice, well-behaved star like our sun is not in thermodynamic equilibrium. And the answer was, I remember it to this day as I'm telling the story, the answer was, you have to start somewhere. So this simple model of assuming local thermodynamic equilibrium is what you start with. And then you add complexity to try to get to where you can deal with the very complicated system that is a star's photosphere.
Right. I mean, that's the joke about the cow being a sphere.
It is. You start out with a simple situation, then you add complexity.
Yeah, and we know that, there are most things in the universe, and including life, are very highly complex systems.
Absolutely.
And it's not just the fact that, we should know exactly how life forms because we're made up of the normal elements you see in the periodic table, but it's the interaction, is the collection of systems and how they operate in a complex way that eventually gives rise to something that we recognize as life, something that's alive, that can replicate and so on and so forth, right? And pass on heredity, their genes, to the next generation, so genetic information, and so on.
Right.
Right. So that's something that a lot of people are working on, is to go from something that's if you like, going from a rock to a human being, right? What are those detailed steps? Although, of course, we don't have those detailed steps today. It's not, and that illustrates the point in science. We don't know everything in science.
Right.
In fact, I would argue most things we don't know about, right? In astrophysics or cosmology, what is the dark energy? What is the dark matter? That represents 95% of the universe in terms of its mass energy.
Look, on my end of things, the stellar astronomy, I'm going to sit there and say we really still don't know how these cold molecular clouds collapse into stars. We know some of how it's done, but we don't know that root, what causes them to start, because as a gas collapses, it heats up. Well, the heating it up should make it expand back out. But that's not what happens. They keep collapsing until they form stars.
Or you could hypothesize that stars don't exist because your simulations didn't make any.
Right. You could say that. Stars don't exist.
But then you put your eyes away from your computer screen and look up in the sky at night.
And there are stars.
Then you're like, dope, the old Homer Simpson thing. And you're back to the drawing board you have to go, right? Because stars exist.
So we're still trying to work this stuff out. But we're getting there a little step at a time.
Now, the formation of stars, that's something that we study when scientists look at what we mentioned in this paper with the methyl cation in the Orion Nebula. So we want to bring up slide number 2.
Yep.
So this is the observations from the James Webb Space Telescope of the Orion Nebula. You can see on the left side, this is sort of a wide field image. And we zoom in on that area that's highlighted in the box. It's towards the upper right. That's what you see up in the top right panel. And we can zoom in further into the box that's sort of roughly in the upper middle, and that's the one you see in the bottom right. And that's one of these protoplanetary disks. Yep. And you can see it's sort of outlined in yellow the way the color scheme is. These colors are all fake. Yes. These are colors that are put in the image to allow you to see the different features, right? Contrast differences.
Let me add something there. The image is not fake, but it is in infrared light. We don't see infrared light. So the color has to be added so that we can see it.
Yeah, so it's just a way of allowing to visualize the different features that we want to see to make them stand out.
And that's what they do too, is they'll change the color scheme they use to highlight certain features.
Right. So the protoplanetary disk in this image then in the bottom panel on the right, you can see sort of a bright spot there near the center. That's the host star that's forming today.
Right.
So that's just a very, very young star. And you can see the darkness that's sort of to the bottom a little bit. And that's the edge-on view of the protoplanetary disk that's in the process of formation.
So what's all the other orange and yellow?
Yeah, so a lot of that star, the orange and stuff, it's all in the background because it's embedded within this giant molecular cloud. So that's just the background features.
It's also glare of the light off of the dust and things like that.
Right. So that what you need to concentrate is kind of the thing that's outlined in yellow, just the way the color coding that they use. And that's the feature that this measurement is coming from. So we measure then these, if you like, these molecules, right? These pre-existing molecules that allow you to get eventually to amino acids and DNA and protein and these sort of things that we need for life as we know it here on Earth.
So, and infrared is a good place to look for the spectra of these molecules, by the way, because here I want to be able to see us. Because the neat thing about organic molecules is they're usually long chains of carbon atoms. And so they vibrate, they pulsate in and out, they rotate around each other, they flex. And all of these things produce spectral lines that identify the object. Well, most of them are in the infrared or microwave wavelengths. So infrared and microwave are where we want to be looking at to see these things.
That's right. And even to see the structure in the protoplanetary disk, because it's embedded within a giant molecular cloud, which consists of dust and gas, to be able to penetrate through that, to see the light coming from the deep interior of it, you need to go to longer wavelengths. Because the longer the wavelength, the more easy it is for photons, particles of light, to pass through that material.
Right.
So it's the shorter wavelengths that get scattered and absorbed more so than the longer wavelengths.
And I will point out that anybody who's been out in the woods, hunting or otherwise, knows this trick. Because how do you, when people are close by, how do you identify that you're there? You raise the pitch of your voice, because short wavelength sounds carry well. They're sharp, they're staccato, okay, as my music friends would say. Longer wavelengths, though, when you drop the pitch of your voice, carry a lot farther because they're not scattered around the trees and everything. Right. So you can see this effect or hear this effect with sound or with any type of wave.
Yeah, in fact, you can just look up at the sky on a beautiful sunny day. That blue sky is a reflection of, no pun intended, of the fact that it's the shorter wavelengths that get scattered preferentially,
Right.
given our composition of our atmosphere, of the gas and dust particles that it contains, than the longer wavelengths. In fact, in the summertime, we have a lot of smoke in the air from forest fires. And that would cause the sky, if you look at the sun, even at noon, local noon, to look red rather than its normal yellow in color that we perceive it.
In fact, a couple of weeks back, we had enough smoke in the air it was obvious. I mean, you could go out and look at the sun shining on the floor in the windows and recognize that it was orange or redder than it should be.
Right.
So it's like, yeah, these things happen and you can experience and observe them on your own.
Right. So when you're looking in these star formation regions like the Orion Nebula, then now we're seeing signs of a lot of these basic building blocks that we need to form life as we know it. Now, I always say as we know it because, once again, it's a sample bias of one.
Sample bias of one. Right.
And we don't know of life anywhere else. We haven't discovered living things anywhere else. Okay?
Right.
So maybe there's other forms of life. But, from the point of view of fundamental physics, you can kind of narrow down what is the range of parameters or properties that would allow life to form.
Right.
Right? So one thing is, for example, that is it all carbon-based, or for example, can you get to silicon-based type of life forms?
Our phosphorus. Phosphorus is a good choice because it's highly energetic, kind of like carbon, but it doesn't form as wide a range of chemicals. But it is there. Your body even uses phosphorus. ATP, the power that powers your cells, is the P stands for phosphorus, a phosphate.
Right. Well, remember recently the discussion about phosphine in the atmosphere of Venus, that there's a lot more there than what should be there, and that it may be a reflection of life on the planet.
Right.
And so that became very interesting for a while, and then people looked at that, and some people said, no, it's
perfectly within natural parameters.
Right, a geological type of events. There is volcanism, and a lot of volcanism on Venus itself. It's like 80% of the surface of Venus is covered in volcanoes.
But you know what I say? Poke at it.
Yeah.
It's worth looking at.
Well, we are going there, right? So
Right.
we have another mission that's being prepared to go to Venus in a few years. And
Right.
so, there'll be follow-up missions if there's any evidence at all that there's something interesting occurring related to life in the atmosphere of Venus itself. So
Yep.
that's one of the things. And Venus is relatively close, so we really don't need to. It's not like you got to wait 15 years to get to the outer solar system, right? You
Right.
can do it in a few months, right? Less than a year, depending on how many flybys and then what is the size of the rocket that you're prepared to use.
Well, the neat thing about Venus is you can use aerobraking to get
Right.
things into orbit. You don't have to carry enough fuel like not the Parker, Magellan had to do with Mercury, where it had to carry enough fuel with it to pull into orbit. With Venus, you can just fly through the upper layers of its atmosphere and lose enough energy to fall into orbit.
And we've done that in the past.
Absolutely.
So it's not like it's something that science fiction. It's science fact.
I mean, we've even done it on Mars.
Yeah.
So
And that has very tenuous atmosphere, so a little bit more difficult. You have to do a lot more work to get it to the speed that you want it to be going at.
you got to do a few more passes. That's how they did it, by the way, they kept doing it till finally they settled into the orbit they wanted.
Now, if you want to go to slide number 3, Robert.
Sure.
Now, there has been, over the years, evidence for the basic building blocks of things like amino acids. So amino acids are essentially composed of things like carbon, nitrogen, oxygen, hydrogen, even some 2 of the 20 amino acids that are in our bodies are made of
Right.
sulfur.
Right.
Okay? And these amino acids then help build up, or construct the protein. And it's the protein and the nucleic acids that we need, to ultimately get to RNA and DNA
Right.
and eventually into life, right?
Proteins and enzymes. So, usually the step goes, you have amino acids, which have that nitrogen amine group on it. And then they form chains called polypeptides. And then the folding of those polypeptides are how you get proteins.
Right.
And so, it all starts though with these basic that you're seeing, and quite a few more organic molecules.
Right. So this slide shows you in the background is an outline, a nice image taken of the Green Bank Telescope in West Virginia. So this is a radio telescope that's about 100 meters in diameter across, and it's the largest fully steerable radio telescope in the world now. It's just slightly bigger than the one that's in Germany. So this has the record. It's relatively new because it was built after the collapse of another radio telescope at the same location here. So they built this one.
So this is a fairly new
New telescope. Yeah.
Another little fun story, fun little tidbit. I remember Green Bank mainly because there's a radio blackout zone where they can't put microwave towers for your cell phone or anything else. In fact, you're not supposed to bring cell phones at all into the area, because it will interfere with the observations of the telescope.
Yeah, that's one of the things about radio telescopes. They're very sensitive to any type of electrical noise.
Mm-hmm.
So even cars passing by on a highway, like the spark plugs that are firing, that electromagnetic radiation can get in the side lobes, as we call it, in from the side of the dish and be picked up by the detector.
Used to be the bane of our existence, because the radio waves that are produced by your spark plugs used to be able to be picked up by your radio. So you'd have this constant in your radio.
An AM radio.
AM radio, yeah.
And the other thing that when you're using a radio telescope, you got to watch out for is any kind of electrical discharge from lightning storms.
Mm-hmm.
So if lightning storms are within so many miles away from the facility, you have to essentially shut down, because the electromagnetic waves can be so powerful that they would actually, destroy the detector, which is actually built to detect very sensitive type of signals coming from space.
Right.
So you could easily, saturate the detector and cause some real damage.
I'm kind of glad you brought that up, because that's another thing about James Webb. people are like, why does it get such lousy views of the planets? And it hasn't really, but, Jupiter did a phenomenal job on, but you also got to remember it was designed to look at faint, far away objects. So something close and bright, like the planets in our own solar system, are of course going to be horrible images full of glare and diffraction spikes and all of this type of thing. It's going to look like an Abrams movie, J.J. Abrams.
Well, the way James Webb is put together with its different segments, when you're looking at fairly bright stars, when you look at the data itself, they have a really weird, what we say in astronomy is a point spread function.
Right.
And the point spread function itself is what you'd expect it, but they have these weird features around the objects, and that's because of the
glare.
The mirror was put the very bright sources and how the telescope was constructed.
It was not made to look at bright objects. It was made to look at faint things that were far away.
Put it this way, when I look at a fairly bright star and an image from the James Webb Space Telescope, I can certainly tell it came from that telescope just by looking at it. I don't need anyone to tell me. Just because it's so unique, the pattern of the light that you see around it. Now, in this particular image, as I mentioned, you can see the Green Bank Telescope and also the different types of molecules that you're seeing here. These are precursor molecules. That's what I wanted to point out.
Oh, okay. Yeah.
So these are the things that you need that eventually would be combined together to give you things like amino acids and DNA and so on. These all were discovered from their spectral lines or emission lines by this particular radio telescope.
Mm-hmm.
Now you might ask how many of molecules in general have been discovered out in space. The answer is it's hundreds of them.
It's hundreds. And I looked it up before the show.
Yeah, and increasing all the time.
Right.
As we build, look in different regions and build more sensitive devices and so on. And so we've literally seen hundreds and hundreds of molecules in the interstellar medium.
Right.
Whether it's these giant molecular clouds or in other areas as well. So there's lots of molecules out in the space.
Right.
They're not just, here in our own solar system for some reason.
These we're talking about the ones that go into forming life. So there's plenty of benzenes and phenols and all of these. They've been seen. Their spectral lines are there in the radio, microwave, and infrared.
And there's even alcohol, the kind that you can drink without going blind.
There you go.
Unless you drink a lot of it.
Unless you drink a lot.
Then you probably would go blind, right?
And then you'll probably go blind because you're probably, holding your daisies.
Yeah. But if you go to the next slide, then this is an interesting announcement that was made just a couple weeks ago. And this is the discovery then of an amino acid. It's not a precursor to an amino acid. It's actually one of the amino acids. And this is known as tryptophan. And this amino acid was discovered in a star cluster in the constellation Perseus. And for those who like names of things, it's IC 348. Now, this type of amino acid, you know what that does for us?
Yes, it makes you sleepy.
It makes you sleepy. So if you have too much of this, maybe you nap all the time. I don't know.
I was about to say, this is one of the amino acids found in some quantity in turkey.
Right, yes. Okay.
So
yes.
it's responsible. It's why you feel, well, it's one of the reasons you feel sluggish and everything after your turkey dinner on Thanksgiving.
Well, some say that's a myth, but I don't know.
Well, there is a higher than normal concentration of tryptophan.
Maybe it's all the
But it's
turkey and the
also-
potatoes and vegetables and having overfilling your stomach
Right.
that makes you tired, right?
Right.
I guess you could overfill your stomach on pepperoni pizza, you'd still be tired, right?
There you go.
So
So it's a myth, and that, yeah, it's probably got more to do with the fact that you stuffed yourself and your body is pulling blood in. But tryptophan is known to make people drowsy.
right, and this is not in the Orion Nebula. This is in a different area.
Oh, wow.
Right.
So
So-
it's not been found in Orion.
Well, I don't know. This is the first finding of this was data taken with the Spitzer Space Telescope, by the way.
Oh, okay.
Right. So this was, lines that were all intents and purposes came from this type of amino acid, the spectral lines that was discovered. So what I'm trying to illustrate is we just don't have to go to the Orion Nebula, and that's the only place you find all these things. They're found all over the place.
Right.
All of the giant molecular clouds and star formation regions, we see signs of the precursor molecules or even the amino acids themselves are located in the various things.
So,
So, also another place where amino acids have been found in?
well, and you mean besides us, right?
Right.
Okay.
Things that came from space, directly from space.
Oh, yeah, meteorites.
Meteorites. And guess what I happen to have in my hand, Robert?
Woo.
I happen to have a meteorite. Now, I don't know if it's going to focus in on that. This is a stony meteorite that I purchased. This was actually fell in northwest Africa. Okay.
Mm-hmm.
Now, meteorites like this have been found to contain amino acids. In fact, we actually found some too also in
Cometary material.
yeah,
yes.
we had probes sent to, right?
Yep.
And then people scoop up that atmosphere, comet or asteroid-like structures, right? There's, it's really, nowadays there's no clear distinction between comets and asteroids because we find a lot of objects in our solar system that are asteroid-like, but then they have small tails when they get closer to the
Right.
sun. So there's like this mixture that can happen, this continuous type of classification rather than separate, discrete objects. Right.
That brushes up against something else, but it's not relevant to the topic, so I'll refrain.
So we find amino acids then within even asteroids within our own solar system. So what we could probably say is that these things are everywhere, right? They're not just locked here on the Earth, and it's the only place, that you're going to have eventually forming RNA, DNA, and then complex life sort of things. That these things are ubiquitous, that we find them all over the place, that they're extremely
Right.
common. In fact, our whole notion of this is probably going to shift, it's sort of a paradigm shift in our understanding, going up very much like what we had where we thought the only planets that existed was planets around our own sun. There weren't no other solar systems. And some people, suggested that.
Right.
Where that's not true. We find essentially almost every star statistically has at least one planet, if not more.
Right. I was about to say, and unfortunately, we've had people burned at the stake for saying.
Yeah, Bruno, I guess you're
Bruno.
thinking about.
Yeah.
What year was that? 1600 or something
1600, sometime in the 1600s. Yeah.
Right.
It was it was before Galileo because
Right.
they at least stopped burning people, or at least well-connected rich people who made such statements.
Well, I don't know. It depends where you are on the Earth today.
Right. That's true too.
I'd be very careful of that.
Yeah.
So,
But since the 1600s, people have been saying, "Hey, there are other planets around all those little twinkling lights," and it was the 90s when we started finding out that yes, indeed, there are.
yeah, the first planet was actually found around a pulsar,
Uh huh.
around a neutron star, which
Around
is
a neutron
very weird in the sense that a neutron star comes from the explosion of a massive star, where you would think that during that explosion, any planets that existed going around that host star before it went supernova would be just destroyed, eliminated.
Absolutely obliterated.
Now, but the other thing that could happen is during this whole process of the supernova explosion, when things settle down, maybe planets formed.
Formed, yeah.
And that's what we're detecting around this particular pulsar. I think there's been another pulsar that we detected planets going around, but it's very rare. Out of thousands of pulsars that we know that exist, there's only been 2, let's say, that have planets.
Right. And I'll go ahead and say it should be fairly easy to find planets around pulsars, because the pulses that they give off are very, 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 very regular in their timing. And so a planet of any size around it is going to jar that timing periodically as it moves around.
The gravitational tugging
Right.
of that neutron star. Yeah.
So, when we say there's thousands of pulsars and we found planets around 2, that's probably a pretty good estimate. So
for sure.
pulsars generally don't produce planets.
Yeah, these are real oddballs. It's just that they were very easy to detect using the method
Right.
you suggested.
And to be perfectly honest, you don't want to be around those planets anyway, because they are going to be bathed in high frequency, small wavelength radiation.
Yeah. So the first planets formed around normal stars was 51 Pegasi.
Yes.
That was the first. And then it was almost like when you're looking for something and you can't find it. Let's say you're looking for one object and it's a family of objects, right? So
Right.
you finally find one of the family, and all of a sudden you see a second member and a third member and so on. Once you find one, it becomes much easier, it seems, to find a lot of them. And so once we found one planet, then it became easy to find others. Right?
And not only that, but you start refining your techniques. You've not only found what you need to look for, but you start refining those techniques, and making them better. So with radio velocity, I know this was the case. We went from only being able to see nearly 100 meter per second variation in the star's movement to now we're down to around 1 meter per second, which is what you'd need to find an Earth-like planet at an Earth-like distance.
Well, there's that, which is development of instrumentation.
Right.
And the second technique we call the transiting of planets method is where a planet would move in front of the host star and block slightly the light coming from that star.
Yep.
And that depends how well you can measure that on how well you can measure the brightness of stars.
Right.
And so we put up very accurate telescopes in space, like the Kepler mission, like the TESS mission that's up there now working, NASA type of missions. They can measure very accurately the brightness of stars, and you just keep repeating those measurements, looking for these periodic changes in the brightness of the dips in a characteristic way that reflects the fact that there could be planets going around that stars.
Absolutely.
And the thing you have to worry about, of course, are things like sunspots, but there we call them star spots.
Star spots.
So if you have a star that you're looking at and it has a sunspot-like activity, magnetic storm on its surface, that will cause the brightness of the star to dim as that star spot swings in the view of us.
In fact, they've studied the rotation rate of stars based on the fact that they can see that dimming.
Right.
So obviously that means we have ways of being able to determine whether it was star spot dimming or planetary dimming.
Right.
And that's also why you cannot confirm a exoplanet until you've made at least two successful observations of it.
And the other thing we can do too is we might wonder maybe the star is just changing in brightness because of its inherent nature.
Right.
Because there are a huge number of stars that we call variable stars that actually change in brightness through various mechanisms.
Right.
And so how do you know you're not just looking at a star that's undergoing these normal periodic change in brightness?
Right. And some of that is the shape of the light curve, because all of the bottom, a planet, because it is much smaller than the star, in general, the star dims and then the planet moves from, so it's flat for a little while, and then it comes back up to brightness as the planet moves in front of it. Whereas two stars are roughly the same size, so star going in front makes this V shape to the light curve. And a variable star, if it's a regular variable, its light curve will be almost some form, well, I'll just say it'll be some form of sinusoidal form. If it's like Betelgeuse, completely non, then it's just all over the place.
Well, don't forget, then we have those other type of details that we look for.
Oh, yeah.
When the planet's in front of the star relative to us, the planet is blocking the light coming from the star, right? When it's on either side of the star, some of the light gets reflected off the surface of the planet back to us, so it adds into the brightness of the star a little bit.
So there's a little bit of a horn.
Yeah, and then when the planet is on the other side of the star, we don't see it at all.
Right.
So that would decrease in brightness slightly from when it's on either side, that we can see the reflected light off of that planet as well as this directly the star itself.
That was recently detected as well, the eclipse of the planet going behind the star. It was a giant planet.
Right. Well, all these higher order features in the light curve is what we're talking about. Those are very characteristic to being planets that are orbiting that star, and not the fact that it's changing in brightness of the star itself, some intrinsic change in brightness of variable nature, or there's some type of star spots that are on the surface of that photosphere of that star.
And in the end, we also like using multiple methods to detect these planets. So the best case is when we can get a transit and then follow up with radio velocity, where we pick up the wobble of the star, because then we can get almost dead on the mass of that planet and some other aspects of it as well.
Well, just think of our sun, and just have our sun and Jupiter. Don't think of any of the other planets in our solar system. Now, as those two objects orbit, what's actually happening? They're orbiting around the center of mass.
Right.
Jupiter is not orbiting around directly the very center of our sun.
Right.
Okay? Because we know Jupiter pulls on the sun via gravity, and the sun is pulling on Jupiter. Yep. So they orbit around the center mass. Think of a seesaw or a teeter-totter. You look for that balance point. If you have people of equal mass on either end, and you're exactly in the middle, it should be horizontal, right?
In this case, though, the fulcrum, the pivot point of that teeter-totter is very much towards the sun.
Yeah, for sure, because it's much more massive than Jupiter. So when you throw in then, so in other words, if you just isolate those two bodies, then if you just looked at the sun is not stationary.
Right.
It is orbiting around the center of mass. So because that point is inside of the sun, when we just include Jupiter in our sun, then the sun wobbles.
Right.
Now, if you throw in Saturn, if you throw in Uranus and Neptune and Mercury and Venus, so you throw in all of the complexity of all the other planets and objects in our solar system, the sun undergoes this sort of complex motion that it's orbiting around what we call the barycenter of the solar system.
Right.
Sometimes that barycenter point is inside of the sun, and other times it's outside of the photosphere, outside the surface of the sun. Still close to the sun, but outside of its surface, given the positions of where all the planets are at some period of time. So we can actually see that complex motion, the wobbling motion. We can detect that. Well, if we can detect that, then if you're in a spaceship, let's say 1 light year away, and you have a telescope with a sophisticated enough instrumentation with that telescope, you can also detect the wobbling motion of our own sun.
And you know there's planets.
And you know there's planets. In fact, you would come up with estimates of how many planets, roughly, what are their masses, roughly, these sort of things. So you can't hide the fact that our sun has a system of planets.
Right.
And therefore, possibly life. In fact, it may catch the attention of some life form. So they would swing their big telescopes towards us and look to see if they can detect the composition of the atmosphere of the Earth when it goes, or it's orbiting around our sun. When the light passes through the atmosphere, there are spectral features that get imprinted on that starlight. And if you had sophisticated enough equipment, you can see those type of features. So imagine you're a life form on a planet that's about 4.2 light years away in the Proxima Centauri system.
Okay.
You look at the Earth as it orbits. You don't know it's the Earth, of course. There's some planet orbiting a star. And from the analysis of the atmosphere, of the composition of that, you see signs of chlorophyll. What does that tell you about the Earth?
Well, it means there's at least something that's photosynthesizing.
There's life.
There's life
on that planet. And at that point in time, you may discover for the first time there's evidence of life other than the planet you live on in that Proxima Centauri system.
Yep.
And that happens to be in the sun on some planet, the third one from the sun.
Yep.
You see?
Absolutely.
Now, if they can do that to us, we can do that to them.
Right.
With the right telescope and detectors, we can sniff, we
So-
can analyze the atmosphere of these planets
So-
and see if there's evidence for life that way. Right?
So what type of molecules do you look for when you're looking for this sort of thing?
Well, oxygen is one.
Oxygen is one. Yeah, that's the one I was looking for.
Yeah.
Oxygen, for those of you who don't know, is very reactive, incredibly reactive. It will not exist as oxygen for very long unless something is replenishing it.
Right.
Yeah.
So the early Earth never had an oxygen atmosphere.
It all combined with the rocks. It all combined with other gases in the atmosphere. Oxygen does not exist on its own for very long. Another one you're looking for, methane,
Right.
because it quickly photoionizes into other organic molecules. So if you see methane there, something is replenishing it.
Right. So oxygen was poisonous to life forms in the early part in the history of the Earth.
Right.
And then it was only through the evolution of life. Remember, this is a science podcast, so I can use the word evolution,
Right.
even biological evolution, that eventually life forms appeared on our planet that actually use oxygen, that requires the presence of oxygen. And that's in modern times, more recent times.
And we still have some of the old type of life on our planet. And people go, what are you talking about? There's a reason when you want to make beer, well, you have to keep it airtight and sealed while you're making it because the yeast is anaerobic. It doesn't like oxygen. There are other anaerobic bacteria and fungi. They die in the presence of oxygen. So that old life is still with us.
Well, I'm gonna if you're more interested in this topic,
Absolutely.
to understand, what are the different things and changes that occurred to the Earth over its last 4.5 billion year history that ultimately leads into animals on this planet as we have today. One of the things I want to suggest, I'll put in a plug for a book
Okay.
that's actually full of the nitty-gritty detail in this sort of thing and written in a way that's very understandable. It's a book by Peter Ward and Donald Brownlee. It's called Rare Earth. So here's the book here. Now, the process or the purpose or motivation behind or the major theme of this book is that all the conditions that you need to have complex life, animal life like us here on this planet is very rare. The probability is very low.
Very low.
Not to have life, that probability is not so low, rare, but to have the animal life that we have that can build spacecraft, for example, and explore our solar system is extremely rare. They make an argument for that. So, and you can see that argument outlined in this book.
I got to admit, I may get the book, but I can buy that argument. I mean,
Yeah.
I always pointed out to people, this 3-pound lump on top of our necks takes 1/3 of your caloric intake to run. If that doesn't provide a survival advantage, it ain't developing.
Right. And this book is a good way of kind of looking at all the factors that are involved in looking at a situation like that. It basically going from what we talked about at the beginning of the podcast, how do you go from rocks to life, right? How do you go from, for example, this to this?
Yep.
What are the steps involved in detail?
Yep. And we don't know yet.
And we don't know. And
But
it may,
come find out.
right. And
Join
one of the
us.
ways you can find out is explore biology.
Right.
Get into the science.
Get into the science.
Right, and explore, the different things and the wonderful advances that are being made, whether it's in biology, in fundamental physics, in chemistry. All of these things are open, and there's a lot of work that needs to be done to further our understanding, not only in biology, but all the other topics and issues that are left right now a complete mystery to us.
Absolutely.
So
yeah.
Now I guess it's time to think about wrapping up today.
Yep.
So Robert, first of all, I'd like to say that our next podcast is not next Tuesday because that's the July 4th holiday. In fact, the university is closed. And I'm not even sure if you're allowed in the university buildings when they're closed from insurance reasons. If you slip and fell, would they cover you?
And the answer is no.
Yeah, they say, well, you shouldn't have been there. The building was locked up and closed. What are you doing there?
Right.
So our next podcast will be Tuesday, July the 11th.
Right.
At 3 p.m. Central Daylight Time. As I mentioned before, if you're interested in science, if you're interested in furthering your understanding of the STEM field or even in arts, humanities, all of this stuff makes us human.
Makes us human.
then consider taking courses here at the University of North Dakota. You can do so online, so you don't have to physically be here in North Dakota.
Right.
If you're in your mansion somewhere in South America, then you can take courses from our university. Or if you would like to drop by or in the area, please feel free to take courses on campus, and maybe you get to see Robert and I.
Yeah.
We'll meet you in person.
I was about to say, if you are on campus, stop by and see us.
Now, Robert, we always leave a quote at the
All
end.
right.
Today's quote, instead of from a well-known scientist, it's from a well-known movie actor / comedian.
Okay.
You ready for it?
All right.
And that quote is by Woody Allen.
Woody Allen. Okay.
So you know it's going to be a good one anytime you
be a
hear
good one.
his name being suggested. So here it goes. So the quote from Woody Allen is this: "Photons have mass? ? I didn't even know they were a Catholic."
Oh,
Thank you
geez.
very much for listening. We'll see you next time.
Bye, folks.